Input-output hardware. Incredible variety of input-output device is storage, transmission, and human interface. Common concept of I/O hardware is signal from I/O device interface with computer. Port connection point for device. Bus, which is daisy chain or share direct access. Then controller, which is host adapter. Electronic that operate port bus device. Sometimes integrated, sometimes separate circuit board, sometimes contain processor, microcode, private memory, bus controller, and so on. Some talk to peer device controller with bus controller, microcode memory, and so on. This is the example of port, bus, daisy chain, and host adapter. This is PC bus structure, which is have a monitor, graphic controller that connect with PCI bus, processor, bridge memory controller, cache, memory, SCSI controller, IDE disk controller, expansion bus interface, keyboard, parallel port, and serial port. All of this is a structure of PC bus. I/O interaction control device. Device usually have register where device driver place command, address, and data to write or read data from register of the command execution. Data in register, data out register, status register, control register. Typically 1 to 4 bytes of FIFO buffer. Device have address used by direct I/O interaction, memory map I/O. Device data and command register map to processor address space, especially for large address space graphic.
Polling for each byte of I/O. Ready busy bit from status register until 0. Host sets read or write bit, and if write copies data into data out register. Host set command ready bit. Controller set busy bit executes transfer. Controller clear busy bit, error bit, command ready bit when transfer done. Step 1 is busy wait cycle to wait for I/O from device. Reasonable if device is fast, but inefficient if device slow. CPU switch to other tasks, but if miss a cycle data overwritten loss. Interrupts. Polling can happen in 3 instruction cycles. Read status logical and to extract status bit, branch if not 0. How to be more efficient in non-zero infrequently. CPU interrupt request line triggered by I/O device. Check by processor after each instruction. Interrupt handler receive interrupt. Must able to ignore or delay some interrupt. Interrupt vector to dispatch interrupt to correct handler. Contact switch at start and end based on priority. Some non-messable. Interrupt chaining if more than one device at same interrupt number.
Interrupt mechanism also used for exception in terminate process, crash system due to hardware error. Page fault executes when memory access error. System call execute via trap to trigger kernel to execute requests. Multi-CPU system can process interrupt concurrently if operating system designed to handle it. Use for time-sensitive processing, frequent must be fast. Direct memory access. Used to avoid program I/O. 1 byte at a time for large data movement. Requires DMA controller. Bypass CPU to transfer data directly between I/O device and memory. OS writes DMA command log into memory. Source and destination address, read or write mode, count of byte, write location of command block to DMA controller, bus mastering of DMA controller, grab bus from CPU. When done, interrupt to signal completion. This is the DMA controller. This is 6-step process to perform DMA transfer. Have a DMA bus interrupt controller, memory, cache, CPU ID this controller in a PCI bus. Application I/O interface. I/O system call encapsulate device behavior in generic class. Device driver layer height difference among I/O controller from kernel. New device talking already implemented. Protocol need no extra work. Each OS has its own I/O subsystem structure and device driver framework. Device vary in many dimensions, which is character, stream or block. Second, sequential or random access. Third, synchronous or asynchronous or both. Fourth, shareable or dedicated. Fifth, speed of operation. Sixth, read-write, read-only or write-only. This is I/O subsystem structure. I/O architecture. I/O subsystem will typically include block of memory dedicated to I/O buffering, I/O bus, I/O device, specialized interface, for instance for keyboard and monitor, and interface card. Possible other connection such as network, cable, and others. This is a kernel I/O structure. Have two sections, hardware and software. At software, have a kernel I/O subsystem, and hardware as you can see at the picture. Characteristic of I/O device. Have an aspect, variation, and the example at the photo here. Block and character device. Block device include these drivers, which is command include read, write, and seek. Raw I/O, direct I/O, or file system access. Memory map, file access possible. File map to virtual memory and cluster brought via demand package. DMA. Character device include keyboard, mic, serial port. Command include get, put. Libraries layer on top low line editing.
Network devices. Variant enough from block and character to have own interface. Unix and Windows NT 9X 2000 include socket interface. Separates network protocol from network operation. Include select functionally. Approaches vary widely. Pipe, FI, FOS, streams, queue, mailboxes. This is socket interface. Each process send, receive message to from its socket. Socket analog to door. Sending process show message outdoor. sending process rely on transport infrastructure on the other side of door, which brings messages to socket the receiving process. Clock and timers provide current time, elapsed time, timer. Normal resolution about 1/60 seconds. Some systems provide higher resolution timers. Programmable interval timer used for timing periodic interrupt. This is 82C54 programmable interval timer. Blocking and non-blocking I/O. Blocking, process suspended until I/O completed. It is easy to use and understand. Insufficient for some need. Non-blocking, I/O call return as much as available. User interface, data copy buffer. Implement via multi-threading. Return quickly with count of bytes, read or written. Select to find if data ready, then read or write to transfer. Asynchronous, process run while I/O execute. Difficult to see. I/O subsystem signals process when I/O completed. This is example of two I/O methods. Kernel I/O subsystem scheduling. Some I/O requests ordering via per device queue. Some OS try fairness. Some implement quality of service. Buffering. Store data in memory while transferring between devices. To cope with device speed mismatch. To cope with device transfer size mismatch. To maintain copy semantics. Double buffering. 2 copies of the data. Kernel and user varying size, full being processed and not full being used. Copy on write can be used for efficient in some cases. Kernel I/O subsystem. Caching, faster device holding copy of data. Always just a copy. Key to performance, sometimes combined with buffering. Spooling, hold output for a device. If device can serve only one request at a time. As example, printing. Device reservation, provides exclusive access to a device. System calls for allocation and deallocation. Watch out for deadlock. Error handling. OS can recover from this read, device unavailable, transient write failure. Retire a read or write, for example. Some systems more advanced, Solaris FMA AIX. Track error frequency, stop using device with increasing frequency of retriable errors. Most return an error number of code when I/O request fails. System error log, whole problem report.
Input-output protections. User process may accidentally or purposefully attempt to disrupt normal operation via illegal input-output instructions. All input-output instructions defined to be privileged. Input-output must be performed via system call, which is memory method, and input-output port. Memory location must be protected too. This is how use of system call to perform input-output. For the first one, this is the diagram. Okay, as you can see, the first one track to monitor, then perform the input-output. Then the last one is return to user in the kernel and user program. Kernel data structures. Okay, kernel keeps step into for input-output components, including open file tables, network connections, and character device state. many complex data structures to track buffer memory allocation, and the last one is the two blocks. Some use object-oriented methods and message passing to implement the input-output. Windows use message passing, which is a message with input-output informations passed from user mode into kernel. Message modified as it flows through device drive and back to process. And as you can see now, this is the unit inputs outputs kernel structure. And the last one is the diagram that I want to show you is the diagram of life cycle of an input output request. So this is the diagram, as you can see. Okay, so in I/O, or what we call it, input output, there is a term we call it stream. So stream is a full duplex communication channel between a user level process and a device in Unix system 5 or in Roman V and beyond or above. So a stream consists of stream head interface with the user process. Second, the driver and interface with the device, and 0 or more stream module between them. Each module also contains a read queue and a write queue. Message passing is used to communicate between queues. Flow control option to indicate available or busy. Asynchronous internally synchronous, where user process communicate with stream head. So there is what we call the simple stream structure in a diagram form. So as I explained, the first is from the user process and going to the stream head and go to the write and read queue, and the final stage is the driver end to the device. Okay, so the next thing we should talk is performance in I/O. So I/O a major factor in system performance. The first is demand CPU to execute device driver kernel I/O code. Next is context switch due to interrupt, data copying and network traffic, especially when it becomes more stressful. So here's the simple intercomputer communication diagram. So speaking of performance, there must be a way that we can improve the performance more better. So the way to improve the performance, the effect of improving performance is reduce number of context switch, reduce data copying, reduce interrupt by using large transfer, smart controller and polling, use DMA, use smarter hardware device, balance CPU, memory bus and I/O performance for highest throughput. LOL. Use DMA or direct memory access. Use smarter hardware device. Balance CPU, memory, bus and I/O performance for highest throughput, which is we can do more multitasking. Yeah, like that. And the last but not least, move user mode process or daemon to kernel thread. So we also have device functionality progression in a diagram below. atas, above.